Alright, so next up in chapter 1 we've got section 1.2 on graphs and lines, and we'll see in a moment that this is very closely related to what we've been doing already on linear equations, because the functions that represent these straight line linear graphs are indeed given by linear equations. And what I have behind me here is just a Cartesian plane drawn on the board, so I've got my x coordinate, my y coordinate, or my x axis, my y axis. I've indicated here the origin, so it has coordinate 0, 0. And I've drawn, or at least attempted to draw, a straight line on these coordinate axes. And I want to point out that when we're working with these straight line linear graphs, there's usually 2 points that we're interested in. In fact, maybe it's not true for just linear graphs, but really for any graph. This point right here, where my straight line cuts through the y-axis, this is usually called the y-intercept. So often worth knowing. And this point right here, where it cuts through the x-axis, is the x-intercept. Let's see if I can fit it on there. There's the x-intercept. And is there anything else I want to indicate? Well, you'll notice that as I move from left to right on this function, on this graph, it's sloping upwards, right? So this has positive slope. So we always read slope as reading from left to right. If I drew another line on here, something like this, that would be a downward sloping graph, so that would have negative slope. And what I want to do, first and foremost, is compute the slope of one of these straight line graphs. So calculating slope. So what is slope? Well, for starters, let me just introduce a name for this. Again, mathematicians are lazy. Instead of writing the word slope, we tend to just use a letter. And the letter we tend to go with is m. So forevermore in this section, I'll denote slope as m. But how do I compute this? What is slope? Intuitively, what is slope? Well, slope is somehow, it's a measure of how much you go up as you move across. Right? In other words, it's a ratio. It's a ratio of exactly what I said. It's a ratio of the rise over the run. So to compute slope, you need to know the coordinates of 2 different points. Maybe I'll call this point, let's say this has coordinates x1 and y1. And this point, we'll say this point has coordinates x2 and y2. So then the total change in the x coordinates as we move from one point to the other, this distance here, what is that distance? Well, on the right, the x coordinates of this point is x2. On the left, I've got the x coordinates of this point is x1. So this distance that I'll call the run. So we're computing rise over run. Computing rise over run. Well, as we can see, so the run, the change in the x coordinates would be x2 minus x1, right? So on the bottom here, I'm just doing the denominator first, x2 minus x1. And on the top, we've got the rise. Well, the rise is the change in the y coordinates, right? So what is this distance? Well, this distance, which is the rise, would be this y coordinate. So this height up here is y2 minus this y coordinate down here, which is y1. So the rise is y2 minus y1. Okay, so our slope, this is the formula for slope. You need to know 2 points. You need to know the coordinates of 2 points. But once you have them, if you want to find the slope, all you have to do is take the difference in the y coordinates over the difference in the x coordinates. So we'll do an example. So we're given 2 points. We're looking at the line through the points 3, 1 and 5, 4. It's not necessary at all that I do this for this problem, but I'll try to draw this line anyway. So we want to pass through the points 3, 1. So that means x coordinate is 3, y coordinate is 1. Here we'll pretend that's about the point. So here's 3, and here's 1. And it also passes through the point 5, 4. So how about we try to plot this? If that's 3, 5, maybe about here, and 4 much higher up. How about up there? There's 5, 4. So there's 4. And we're looking at the line passing through these 2 points. So there's of course a unique line that passes through 2 given points. It's this line. So what's our slope? Well, slope is m, and all I have to do is take the difference in the y coordinates over the difference in the x coordinates. So this would be, say, y2, and here's y1. So my difference in the y coordinates, 4 minus 1, over the difference in the x coordinates. So here's x2, and here's x1. So that's 5 minus 3. And it looks like this comes out to what? 3 over 2. So this line has slope 3/2. And I want to point out that it doesn't matter which order you go. All that matters is that you're consistent. So I could have rearranged this. I could have called these points x2, y2, and x1, y1, and I would have still got the same answer, right? I still would have done y2 minus y1, so 1 minus 4, over x2 minus x1, 3 minus 5. What does that come out to? Well, that's minus 3 over minus 2. The negative ones cancel, and you still get the same answer, 3/2. So there's nothing special about the order of the points here. I just have to be consistent on my labeling schemes of which point I call x1 and y1 and which point I call x2 and y2. So next up, and what we want to do most of the time in this section, is be able to give an equation for a given line. And before we talk about the general case that we were working with 99% of the times, I want to sort of knock out these 2 special cases very quickly. So first up, we've got horizontal lines. This is just the line here that has y-intercept k, so it cuts through the y-axis at the point 0k, x is 0 and y is k. And what's true about the y-coordinate of any single point on this line? Well, if it's horizontal, the y-coordinate never changes, right? The y-coordinate is always k. It's just x that changes freely. So this is given by a very simple equation, just y equals k. Given by y equals k. So all you need to know is that coordinate of the y-intercept, and there's your equation of the line, y equals k. By the way, what's the slope of this guy? Well, it's neither sloping up nor sloping down, so it has a 0 slope. Slope is 0. And then down here we've got this vertical line, very similar to the horizontal line, except now if you look at the coordinates of any single point on this line, the x-coordinate never changes. The x-coordinate is always k, it's just y that varies freely. So this is given by the equation, well, what's fixed? X. X is k. So all I need to know is x equals k. So all you need to know is the value of the x-intercept, and there's your equation of the graph, x equals k. What about the slope? Well, something like this is positive slope, right? Something like this is even more positive slope. Something like this is even more positive slope. So this guy, you might say this has infinite slope, but infinity isn't really a number, so we're just going to say that the slope is undefined. Alright, so it's not necessarily wrong to think about it as having infinite slope, that's intuitively what's happening, but we're not going to go with the number of infinity because it's not really a number, so we're just going to say the slope is undefined for vertical lines. So let's talk about general lines. How do we find an equation of a general line? So if you remember anything about lines at all, you'll remember this equation. any line that you have, so a general line that looks like this, in this case I've drawn it with positive slope, and I've labeled the y-intercept just because it's important. Any line, so something like this, can be given by an equation of the following form: y equals mx plus b, where m, once again, is what we've been calling our slope, and b is the y-intercept. So it turns out that that's the only two pieces of data you need to know. If you know the slope of the line and you know the y-intercept, then you've uniquely determined the line, and you have a nice equation that represents the line. That is, every single point on this line, every single point with coordinates x, y, are solutions to this equation, this linear equation over here. So this is the slope-intercept form. We'll work with lots of different forms of equations for lines in this class, but this is perhaps the easiest one to use. So we'll do an example. Here's a very simple example. Graph the line given by the following equation: y equals minus 2x plus 1. And you'll notice that it is already given in this form. It's given in this form: y equals mx plus b. So I can read off some important geometric information. I can read off immediately, there's my m, right? So my slope, m, is minus 2, and plus b, my y-intercept, is 1. And there's a few different MyMathLab questions for homework that are just as easy. All you have to do is look at the form and read off what my slope is and what the y-intercept is. But I've gone a little bit further with this. I want to graph this, so let's draw a picture of what's happening here. The y-intercept is 1. That means it's cutting through right here at 0, 1. So we'll just call this point 1, or coordinate 0, 1 if you want. And it's got slope negative 2, so it's sloping downwards, and since we're just sketching this, something like that. Maybe not a very straight line, but our picture should look something like this. If you want the x-intercept, we could easily solve for this. Remember, solutions to this equation are the points on the graph. So if I want to know what my x-coordinate is, or sorry, what my coordinates are for the x-intercept, what am I doing? I'm asking what value x takes on when y is 0, right? So x-intercept, when does this happen? Well, again, I want to know what x is when y is 0. So I'm just plugging in y equals 0. So we've got 0 equals minus 2x plus 1. And now I have a linear equation. I just have to solve for x, right? This shouldn't take too much work. Let's add 2x to both sides. So 2x is 1, which means x, divide both sides by 2, is 1/2. So this point right here is 1/2 and 0. Here's my x-intercept. And you can find all the points on the graph, right? This is what I mean when I say this equation represents the graph, or gives us the graph, is all points on this line are solutions to this equation. So for example, if I want to know the y value here, when x is say minus 2, well, that's got coordinates minus 2, and the y coordinate would be, we'll plug in x equals minus 2. Y is minus 2 times minus 2 plus 1 is 4 plus 1 is 5. So when x is minus 2, y is 5. And so this is what I'm getting at when I say this equation is the equation of the graph, is all points on this straight line are solutions to that equation. So you can find all the points if you want them. Alright, so our next example is find an equation for the following line. And I've drawn the line, so here's our line. I don't usually label my x and y axes, by the way, but there they are, x and y. And here's our line, and we want to find an equation. Well, we know one form of an equation for a line is y equals mx plus b, which means to fill out this equation, to fill in all the blanks, I need two pieces of data. I need b, which is my y-intercept. Well, I can just read that off of this picture, right? My y-intercept is if the coordinates are 0, minus 3, the y-intercept is minus 3, right? So b is minus 3. And the other piece of data I need is m. I need the slope. Well, it's clearly got positive slope visually, but what's my slope? Well, I have 2 points on this graph. And I have 2 very particular points, but all I really need is any two points. I have the x-intercept and I have the y-intercept. So I can compute the slope. M is going to be rise over run, right? So we'll take this as our first point. Well, we'll take it as our second point, so we'll call this x2 and y2. So we're going to take the difference in the y-coordinate. So I've got 0 minus 3 over the change in the x-coordinates. So 4 minus 0. And that's, what is that? That's just 3/4. By the way, visually I know it has positive slope. If you've done something wrong there, if you made sort of a mistake in the way you've ordered things or something, if you got a negative number, you should immediately recognize it can't be negative, right? It must be a positive number. So always check if your answer is reasonable. So this looks reasonable to me. And all I have to do now is plug them in. So here's my equation. Y is 3/4 x plus b plus minus 3. And that's it. All we have to do is read off 2 pieces of data from this graph, the y-intercept, and I suppose we didn't read this off, but we had to figure out the slope as well, and because we know 2 points, we can always compute the slope, as one of the very first things we did in this section. The last example was fairly easy to do because we knew the y-intercept, right? One of those 2 points that we had was the y-intercept, but sometimes you're not always that fortunate. Right, so sometimes you know a point on the graph, but you don't know that point isn't necessarily the point where it cuts through the y-axis. So in that case, instead of using the point or the slope-intercept form, there's another form that's really useful. It's the point-slope form. So this time, we still know our slope m, but instead of knowing the y-intercept, we just know some point, some arbitrary point on the line. Has coordinates x1 and y1. And in this case, an equation for the line is y minus y1, so y minus the y-coordinate of the point that you have, equals m, the slope, times x minus x1, x minus the x-coordinate of the point that you have. And there's an equation, and once you have this equation, you can rearrange it however you want. So let me show you how this works. So we'll start off with a fairly easy example here. Find an equation for the line with slope 5/2 and passing through the point 3,1. Well, there's not a whole lot to this, right? Our slope is 5/2, and we have our point that we've just called in the equation was arbitrarily x1 and y1, but that is 3 and 1 in this case. So our equation is going to be, go back to the point slope form we just had, y minus y1, so y1 in this case is 1, the y-coordinate of the point, y minus 1 is equal to m, the slope, 5/2, times x minus x1. x1 is the x-coordinates of the point that we have, so x minus 3. And there's the answer. There's the equation of, or an equation of this line. So this is an equation in the point slope form. Now you might say, I don't like this form. I like y equals mx plus b. I like it in that form. And indeed, my math lab might often ask you to put your equation in a particular form. Well, that's no problem. If I want y equals mx plus b, I just have to rearrange this. I need y equals, let's distribute this out. 5/2 x minus 3 times 5/2, so minus 15/2. And of course, if I just have y equals on the left, that means I'm adding 1 to both sides. So add 1 to both sides, plus 1. And if we simplify this, this is y equals 5 halves x minus 15 halves plus 1, so minus 15 halves plus 2 over 2 is minus 13 halves. 13 over 2. And this is in slope-intercept form. This one's a little nicer than this form, I think, when you're just working with it algebraically, because, yeah, in both of them you can read off the slope immediately. The slope is 5 halves. But in this one, I can read off the y-intercept much more easily than I could up here. So my math lab might ask for it in that form. It might say give the answer in slope-intercept form. Or, here's another form it often asks for and often gives equations in. Or, I'm going to rearrange this. I'm going to write this as minus 5 halves x. So I'm bringing the x and y over to the same side and leaving the constant over here. Minus 5 halves x, subtract this from both sides, plus y is equal to minus 13 halves. So this is in the form a constant times a plus a constant times b, or sorry, a constant, did I say a constant times a constant a times x plus a constant b times y is equal to some constant c. And this is what my math lab in the textbook sometimes calls standard form. It's not that useful in practice in reading off interesting information off of this thing. If you want to read off interesting information off of this thing, you would want to rearrange it to slope-intercept form. So you'd want to solve explicitly for y, as we do here. But quite often it will ask you to give your answer in this form. It will say give your answer in standard form. So you would just come up with your equation in either one of these forms using one of those equations, point-slope form or slope-intercept form, and then you just rearrange it. So last purely theoretical or abstract example we'll do is, I think this is about as hard as they get, is find an equation for the line through two given points. Alright, so of course I can draw this. I can draw this meaning my line is uniquely determined. Passes through 0, 2, 0, 2, something like this. 6, 3, what's that going to look like? So I'll put this up here. 0, 2, and go across 6 and up 3. 6, 3, we're looking for the equation of this line. And you'll realize that I have enough information here. I have more than enough information. I know the y-intercept, I know a point on the line, all I really need is the slope. But if I have 2 points on the line, I can compute slope as well, right? So let's find our slope. Slope will be the change in the y values over the change in x values, or the difference in the y values over the difference in the x values. So we'll just go this y coordinate minus this one, 3 minus 2, over the difference in the x coordinates, and since I started with this y coordinate, I have to start with this x coordinate from the same point, 6 minus 0. So our slope is 1/6. Again, is it reasonable? Looking at this picture, I'm expecting a positive slope, just slightly positive. 1/6 is slightly positive. And now I can find the equation. Because I'm given the y-intercept, I could go with the slope-intercept form, but I want to do more practice with the point-slope form. So we'll do point-slope. We've got y minus y1. So the y-coordinate of a point. And it turns out it doesn't matter which point you use. We have 2 points. You can choose either one. Choose whichever one you want. Let's go with this one. Let's go with that y-coordinate. Y minus 3 is equal to the slope, m, times x minus x1. Now because I chose this point, I have to go with the x-coordinates from this point, but there we have it, x minus 6. And It didn't ask for a particular form, so this I would call is correct, but MyMathLab will usually specify the form. Maybe it says here, maybe it says put it in standard form. So let's put this in standard form. I need to clean this up. Let's see, we've got y is equal to 1/6 x minus 6 over 1/6 is minus 1, and then we're adding 3 to both sides, so plus 3. So that's y is 1/6 x plus 2. By the way, if it wants point slope form, there it is in point slope form. Or if it wants standard form, then just move the x term to the other side. So this is minus 1/6 x plus y is equal to 2. Lots of different forms for the same line. But that's it. I mean, these are the two very important forms. And all you need to know is either, depending on which form you're using, the slope in both of them, and either any old point on the line or a particular point, the y-intercept. But once you know those two pieces of data, then you can write down the equation of the line. This is really, really important stuff all throughout mathematics. If you go on to Math 151, Business Calculus, lines are absolutely fundamental. Knowing these two equations, the point slope form and the slope intercept form, are really, really important skills that you'll be using again and again and again. So last up, I just want to do an application, a business application of this stuff, or a word problem if you want. Okay, so here's a pretty typical supply and demand type question. We're imagining the situation selling boxes of grapefruit, and we're told that at a price of $12.59 per box of grapefruit, the supply is 595 boxes, the demand is 650 boxes. And at a price of $13.19 per box, the supply now, obviously the price has gone up, so the supply has gone up to 695 boxes, but the demand has fallen as the price has risen, and the demand is now 590 boxes, fallen from 650. So assume we have a linear relationship between price and supply and price and demand, and the question is find the market equilibrium, find the equilibrium point. So let's draw some stuff here. Let's graph this. On the x-axis, let's just put x, and let's plot on the x-axis. Let's plot quantity of boxes. So x will be quantity, and on the y-axis, let's plot the price. And I'm not going to call this y. For price, let's call it p. So it'll be the p-axis now. This will be price. And let's see. Let's deal with supply first. So when the price is 12.59. This won't be to scale at all. We'll just put 12.59 here. 12.59. When the price is 12.59, the supply is 595 boxes, so maybe we'll plot that right here. This will be 595. And let me give you the coordinates of this point too. So that means the coordinates of this point is 595 and 12.59. Sorry, I'm trying to squeeze a whole lot on the board here, so I'm writing kind of small, kind of squished. But there's one supply point, and we're also told that at a price of 13.19, again this isn't to scale, I'll just put it way up here, at $13.19, our supply has risen to what? 695. So maybe I'll plot that way over here for scale. So this is now 695. So this is the point 695 and 13.19. And we're assuming that we have this linear relationship between price and supply. That means if I were to plot the rest of this, all the other points would fall on this linear straight line graph. Alright, so here's my supply line. So first thing I want to do is come up with a, that's not a very straight line, but imagine in an ideal world this should look straight. First thing I want to do is come up with a price-supply equation. So, price-supply equation. What do I mean by that? Well, I mean I just want to come up with an equation for this line that I've drawn. I want to come up with an equation for the straight line. We've been doing that this whole class, right? So what do I need? Well, I already have 2 points on the line, so all I need is the slope. If I have the slope, then I have a point on the line. We can go with the point-slope form. So, what's our slope? Well, I can compute the slope because I know 2 points on the line, right? So we can compute rise over run fairly easily. The difference in the y-coordinates, or p-coordinates in this case, over the difference in the x-coordinates. So let's see, let's take the change in the p-coordinates. We've got 13.9 minus 12.59 over the difference in the x-coordinates. So that is, if I took this as my first coordinate and this is as my second y-coordinate, then I should go with this as my first x-coordinate, so 695 minus 595. And this is, I think, this looks like 0.6 over 100, so that's 0.006. So there's our slope, and that means my price-supply equation will be given by what? Well, I'm going to go with the point-slope form here. So remember, I haven't called this y, I've called it p, so it's going to be p minus the y-coordinate or the p-coordinate of any point that I want. Let's just choose this point. So we'll go with 13.19 is equal to the slope 0.06 times x minus the x-coordinate at that point, 695. And I probably want to write this as just p equals, so let's rearrange this. P equals, we're going to have 0.06x minus 0.06 times 695 plus 13.19. I've already worked out what that is. You can double check this if you want. This is plus 9.02. And again, does that feel right? Does it look right? I would definitely expect my y-coordinate, or my y-intercept, the p-intercept in this case, to be something a bit less than 12.59. Here, in this form, I'm claiming it's 9.02, so it looks like we haven't made any mistakes. I need to save this. I'm running out of space, so how about I write this up here? Here's my price-supply equation. P equals 0.006x plus 9.02. Alright, there you are. We'll save that for later. Now we need to do the same thing, but we need to do the price demand. Equation. Alright, so we're going to play the same game here, but now we're going to work with the demand side of things. So coming back to this, we're told at $12.59, our demand is 650 boxes. So 695, somewhere around here is probably 650. There's 650, so this has coordinates 650 and 12.59. And at 13.19, we'd expect our demand to drop because the price has risen. The demand is now 590 boxes. So up here at 13.19, 590 is probably right around here. Right, there's 590. coordinates 590 and 13.19. Those are 2 points on the graph of the price demand side of things. Once again, we're told we can assume there's a linear relationship between them, so I know that the graph would just be a straight line passing through these 2 points. And this, in red, then, is our demand curve. In white we had the supply, in red I've drawn the demand, and I want to do the same thing. If I want a price-demand equation, I need the equation of this line. Same situation, we can compute the slope because we have 2 points, and using the slope at any point we can come up with an equation using the point-slope form. So our slope in this case is change in the y values, or change in p values in this case. So we'll go 12.59 minus 13.19. Over 650 minus 590. That's, what is that? That's minus 0.6 over 60 is minus 0.01. Like I said, nothing here is drawn to scale. That's a very, very small number, but it is what we would expect. It is downward sloping because it's a demand curve. So that slopes down, and yeah, so far it looks good. So now we just need an equation, and oops, it's not p equals straight away because we're using the point slope form. We've got p minus any coordinate that you want. So we'll go with this y coordinate, 12.59 is equal to the slope minus 0.01 times x minus the x coordinate from this point that we chose, 650. Once again, I want to solve for p. We want to put this in the slope-intercept form. So this is p equals minus 0.01x. Then we've got minus 0.01 times minus 650 plus 1259. Again, I've already worked this out. This comes out to plus 19.09. So our price demand equation is P equals minus 0.01 x plus 19.09. Last but not least, what was the actual question? The question was find the equilibrium point. In other words, when does price equal demand? What is this point of intersection right here? This is what we're looking for. So when do we have equilibrium? Well, we have equilibrium when price equals demand. So how are we going to solve for that? Well, we'll set them equal to each other. So that's all we have to do. We just want to set price, we want to set supply equal to demand. Okay, so we'll go ahead and do that. Set supply equal to demand. We've got 0.006x plus 9.02 equals minus 0.01x plus 19.09. And now we're solving a linear equation. What do I want to do? I want to isolate my x's or group them all together. Let's move them all to this side. 0.006x plus 0.01x is going to be 0.016 x's. And we're going to subtract 9.02 from both sides. 19.09 minus 9.02 is 10.07. Okay, so solve for x. X is 10.07 over 0.016. And this comes out to 625.25. Again, you should ask yourself, is that reasonable? If my answer was 10,000 or something, no, it wouldn't be very reasonable, because I know, looking at this picture, it's somewhere between 595 and 695, and that certainly looks like a reasonable number, right? Right here, my equilibrium quantity is 625.25. Looks like a totally reasonable number. I'm totally out of space, but there is one more thing that we need to do, which is the equilibrium point. So it doesn't want just the x-coordinate, it wants the p-coordinate too, it wants the price as well. So I'm totally out of space, but I'll just tell you what it works out to. This has coordinates 625.25, and if you want the price, well, that would be the p-coordinate on either one of these graphs, because it's the intersection point, right? So just plug in 625.25 into either one of these equations to get the p-value, and it works out to, I believe it came for me to 12.77, which again looks reasonable, right? Somewhere between 12.59 and 13.19. So this worked out to a pretty long example, but hopefully you sort of realize the power between this, and lots of things in nature are linear. So what we're given here in words is really just the coordinates of two different points on two different lines. So we came up with the equations of the two different lines based on the coordinates of the 2 points. And to find the equilibrium point, we're asking, when do they intersect? So how do you find when they intersect? You set the two lines equal to each other. You say, okay, I'm going to set these two p-values equal to each other and find the value for x and make them equal. But we'll stop here. Thanks, guys.